Good afternoon. Welcome to episode 121 of Creative Weekend Talks. I am your host, Supriya Nayaka. Creative is a community driven by curiosity and creativity, aiming to explore knowledge behind the. eh, 1 minute. Creative is a community driven by curiosity and creativity, aiming to explore knowledge behind the textbook. Our tagline, Knowledge Square, reflects our commitment to sharing and expanding our understanding. Today's topic is on intelligent polymer processing to properties. We are honored to have Dr. Kalappa Prashant, PhD, DSc, France, the Dean of Research and Innovation at Adichanchagiri University, Karnataka, as our esteemed resource person. As we embarked on this intellectual journey, we have a question session at the end of the program, and join us every Saturday for our online weekend talks on Zoom. And we live stream our program on our YouTube channel, Creative GBD. Our main focus on non-textual, non-academic, non-syllabus related concepts. And we are very thankful to all our resource person for engaging us with their knowledge. And thank you and welcome. We welcome our resource persons of today's talk, Kalappa Prashant sir, for today's session. And I welcome all the creative participants who are in Zoom and YouTube live streaming watchers. So I welcome one and all, and I hand over to Kalappa sir. Over to you,
Good
sir.
afternoon, Dr. Supriya, and all the creative members who are working towards creating knowledge and also disseminating knowledge. And at the outset, I would like to thank. Am I audible? Hello.
Yes, sir.
Am I
Yes, sir.
audible? Yeah.
Yes,
Okay.
sir. Yes.
So I understand the concept of creative a few days ago when I went through your website. I think I congratulate all the creative team for the phenomenal work which you are doing for the past several years. And today I will be speaking on emerging intelligent materials because nowadays we can see a lot of disruptive materials. Earlier we used to have only one materials for specific applications. Today we have one materials doing multiple work. That is to say, materials being used for many applications or multiple applications. I think in that respect, I just want to highlight how the emergent intelligent materials are coming up and how they are going to change the life of a human being. And to start with, so material science, as you know, it is an investigation of the relationship that exists between structure and properties. And materials engineering, engineers basically they design the materials that have specific properties on the basis of structure and properties. For any materials we use, we need to have structure and properties before applying that material for specific application. So here main idea is to play between structure and properties for various applications such as mechanical, electrical, thermal, magnetic, and optical. So now primarily we know materials means metals and alloys, ceramics, polymers, biological materials, because biological materials are really very important materials in today's scenario because all the hip replacement, bone replacement, organ replacement, everything needs a development of biological materials and also composite materials. Whatever the comfort we are using in our day-to-day life, whether it may be in our home or in our working place or in automobiles, everywhere the composite materials plays an important role. For any materials, whether it is metal, ceramic, polymers, biological materials, or composite, so in understanding of the structure as well as properties is very, very important. And So I think what engineers use all these materials. They select materials for existing properties or apply existing materials for new process and design novel materials for specific applications and investigate structure and properties. We need to understand for any materials structure and properties, thermodynamics, because yes, madam. Hello.
Yes, sir. Any problem, sir?
I think someone raised their hand. So stop.
No, no, sir. No. You can carry on,
Okay.
sir.
So I think for any materials, there should be a trade-off between structure and function. We need to understand both structure as well as the function of specific materials. It may be automobiles, space shuttles, or whatever it is. And we need to understand defect also, whether the defects are good or bad, and behavior at interface, interactions with biological system, etc. So all these things are very important. If you go back to history, early in the early time, the stone, wood, clay, and skin were the materials for human beings. And rise and fall of civilizations gave a better materials and tools and weapons. Uh, and in modern times, we materials are everywhere in our lives: transportation, housing, clothing, communication, recreation, food packaging, healthcare, and many others. Hence, the materials plays an important role in our day-to-day life. And whatever the scientists or anybody who is watching this, they should understand that the development of material as a larger scope, because as we move on with the time and age, the human being requires a lot of comfort and a lot of the materials which has very good functions. Only recently we came to know understanding relationship between structural elements of materials and their properties, because in olden days there was no characterization tools such as SEM, TEM, XPS, and so on. Still, the people used to have a better materials for their livelihood. Today we have all the tools, and therefore we are still able to develop a novel materials for specific applications. And you can see here the rise. And earlier there was materials called polymers, and then metals came, and only again in between 1908, from 1940s to 1980s, there was a downfall of material usage because of world wars and so on. But again, there is an increase of usage of metals, polymers, composite, but in modern terms. Earlier polymers means biopolymers, composites means alloys and something like that, and ceramics means that potteries and so on, whatever they're using in the olden days. But today we have modern materials in the same fashion as olden days. Only recently we came to understand the relationship between structural elements of materials and their properties, and thereby we were able to create novel materials for better application. So then what do we mean by structure? Many levels of structure. So there is a macro scale. You can see there is a multiple carbon nanotubes, micro scale, nanoscale structure, and then atomic scale structure. There is a broad range of length scales from atomic scales to macro scale. It is very much important to understand the behavior of materials at atomic scale. So once we understand the behavior of the materials at atomic scale, we will be able to understand, we will be able to define the function of the materials very well. The new tools to determine the probe structures: nowadays we have advanced microscopy, TEM, STEM, AFM, atomic scale imaging. There is an unprecedented control over imaging and manipulating of matter nowadays. Because of the availability of all these tools, we can design the material based on our requirement. And there is a rational design of new materials such as smart materials. They respond predictably. The way we want it will respond, repair themselves, and there are shape memory polymers. And also we have nanotechnology, where we have top-down approach, bottom-up approach, and materials by design. Then there are a wide variety of materials, as I told you before, with the diverse characteristics that suits to various applications. The metals and alloys, polymers, ceramics, and also composites, engineered and as well as natural materials, nanomaterials. Though material condensation, the properties of the materials, mechanical properties, physical properties, chemical properties, manufacturing properties, because machinability, weldability, formability also plays an important role. And very important thing is cost and availability, because the cost plays in a major role for affordable. It should be affordable to common man. And appearance, service life, and recyclability. Because nowadays, as we move on, three E's are very important. Three R's: reduce, reuse, and recyclable. And whatever the materials today we generate, we should make sure that material is reusable or degradable. Otherwise, again, we are going to create a lot of waste in the nature. Then what are smart materials? That is the today's topic. Material which has the intrinsic or extrinsic capabilities to respond to an external stimulus in a functionally useful manner. Each and every word carries a meaning there. You can see here there is a strip which is being used to check the temperature of a human being or a man. You can see at 37 point between 37 to 38 it shows red color. That means the man is having high fever, or the temperature is exceeding 36, which is the normal body temperature of a human being. So this is responding to an external stimulus, so that the strip is a very smart material. And what are smart materials? There are electrical smart materials for permittivity measurements and electrothermal effects, and that measures the temperature. There is a thermoelectric effect for mechanical stress. There is a sensor, strain sensor, displacement sensor. All these materials, which are everything is interrelated. Piezoelectricity, permittivity, pyroelectricity, each and everything is interrelated whenever you say the smart materials. The concept of smart structure can be described as a system which has intrinsic sensor, actuator, and control mechanism whereby it is capable of sensing stimulus, responding to it, and reverting to its original state after the stimulus is removed. Because if it does not come back to its original state, then it is very difficult to use. It is not possible to call it as a smart material. It should come back to its original state the moment stimulus is removed. And integration of function such as sensor actuators are there. Stimulus can be stress, strain, light, electric field, gas molecules, temperature or pressure. Nowadays you get and the response is very very important. Without the response, the smart materials cannot be used. And the advantage of smart materials is no moving parts, because everything is infixed. We don't have to have a separate material for that. And then high reliability, low power requirement, provide new capabilities that are presently not possible, and they are intelligent, very simple. The passively smart, actively smart, and very smart and intelligent. Passively smart materials are which can only sense the environmental condition or stimuli, just senses, and actively smart which sense and react, and very smart which can sense, react, and adapt themselves according to the situation. Intelligent structures utilize the nonlinear properties of the sensor, actuators, and memory or feedback system to tune the response behavior, which those capable of responding are activated to perform a function in a manual or pre-programmed manner. That is the intelligent. Whatever today we have artificial intelligence or anything happens in the system, and the same thing we can observe in some of the materials in today's scenario. So what are smart products already available in the market? So monitoring, awareness of the status, sensing, the sense of the environment, adaptive, they respond to the stimulus, and the features, the environmentally embedded integrated networks devices, and then recognize the situational context. It is almost everything is related to artificial intelligence, and whatever we see, as I told you before, whatever we see in the system, the same thing is applied inside the material, and anticipate user plans and intentions, so that the material can tune and the machine can understand what exactly need to be done and under the circumstances. A smart materials can be described as a material that has a useful response to external influence or stimulus. So there are many examples of smart materials in everyday use that are not modern development. They include metal springs, for example, metal spring, which is being used since olden days. That is also smart. Whenever there's a hump or something, the spring just adjusts automatically and respond to the stimulus and come back to its original state whenever there is not required. So mirror springs are the best examples for smart materials. And also, light bulbs, they self-regulate because as the filament temperature increases, the resistivity rises. They regulate themselves. Therefore, this can also be called as one of the best example for smart materials. And this is the ancient potteries. Ancient civilizations have long used porous ceramics for self-regulating cooling, because if the cooling is not regulated, then the porosity, because of the porosity, the temperature was regulated in the old civilization. That's why you see the water inside is cool. So other modern examples of smart materials include shape memory polymers. You can see the heat shrink tubing and packing, automobile actuators, and open close greenhouse windows, thermostats for heating control, all are available in the market in today's life. And there is a smart wire that is actuator, a linear, angular, and rotatory, and depending on the size of the apple, it can hold and it can adjust to the volume of the apple. And then smart link silicones, because this shaft allows the rotary motion between the shaft up to 360 degree because of the smartness of the silicone rubber. And nowadays we have smart fluids for motion control gels, CD tray opening and closing, camera lens, ferrofluids for earthquake dampeners in buildings, and hard disk. So there are smart fluids, and nowadays we have nano smart fluids in the market. So piezoelectric materials, sensors, music, and piezoelectric materials, you all know it is already being used in the clocks. And chameleon colors, you can see there is a car paints and printing inks and packaging, and this paint changes with the temperature. So when when it is too cold, it becomes different color. When it is too hot, it shows different color, because it changes its color with respect to temperature. Other more modern examples are thermocolor sheet. You can see here this is a self-devised sheet whose color changes according to the temperature. So you see here the moment you put your finger on the sheet, so human body temperature is 36 degrees centigrade, and there is a change in the color. So that really indicates warning patches, heat warning patches, and novelty advertising of products, and all these materials are already uh, available. You can see this is the beauty. Other more modern example, if you visit any European Union countries, if you see they'll be using heaters. You see the first one, everything is empty. Here nothing is there. Here also, you can see there's a pink color coming up, because once the heater is on, the temperature of the wall is increasing. So once it increases, it gives different colors to the flowers in the wall paintings. So this is a thermochromic materials that activated by heat. And then phosphorescent sheet, this sheet absorbs light energy. And REM emits it is white light for up to 8 hours, and that is extensively used in emergency lighting in the event of the power cut. So, and then lenticular sheet, you see here that it is different. The camera lens does not capture the effect. And then quantum tunneling composites are also available. When compressed, it becomes very perfect conductor. Yeah, when it is compressed, it acts as a perfect conductor. When the compression stops, then it releases. It is not. It is no longer a conductor. It works based on the compression force. And there are many such examples are already available in the in the market, or also if you go through any peer-reviewed journals, you will get a lot of information on this. And as a it is a combination. All this smart material manufacturing is a combination of both. It is a combination of information and communication technology, manufacturing technology, and smart materials. Because if you don't merge these three things, or if you don't map these three things, it is impossible to prepare a smart material. Or you can prepare a materials. If you find application, you need to have information and communication technology incorporated into the smart materials. Then only it can be used in the system, and also it can be commercialized through proper manufacturing technologies. And we have in the laboratories nowadays, there are different color, electric, magnetic, luminescent, electrochromic materials, and the electroactive polymers, which are extensively used in the wastewater treatment, and also as a conducting electrodes and so on. And there are also rheological elastomers, ionic polymer gels, which are being used in pharmaceutical industries, and there are dielectric elastomers, and then there are shape memory polymers. They are thermoresponsive polymers that modifies its shape in response to the temperature changes. I will give you, in my talk, I will give more emphasis on shape memory polymers in few slides of later, and then self-X polymers such as self-monitoring, self-diagnostic, and self-healing. That is very important. Nowadays, there are multi-story buildings coming up. If you want to clean the windows in the outer side, it is highly impossible. Therefore, many construction industries are using self-healing, self-cleaning glasses, and as well as self-healing glasses, because they heal themselves if it is broken after a couple of time, or if there is a dust sits on this and it cleans on its own. So there's a new materials which are already being manufactured in the society. So there are several types, and one is shape memory polymers, second one is self-healing, piezoelectric materials, electrodestructive polymers. So let us see what is shape memory polymer now. Materials that can be deformed and then returned to the original shape, memorized shape by external stimulation. Deformation usually involves elongation, where shape recovery is the contraction back to the pre-stressed length. The effect due to changes in the material structure are unrelated to thermal expansion or contraction. So applications of shape memory polymers includes which is being used in aeronautics, surgical tools, and muzzle wires. Because and the second polymers, what are self-healing polymers? Self-healing is the ability to repair or damage in an automatic and specific fashion without manual intervention. It has to heal itself without the manual intervention of anybody. The ability of a material to be able to heal damage automatically and autonomously is called self-healing properties. Because suppose today, if you launch a satellite, if there is any minor damage in the satellite, it should be able to repair on its own. Otherwise, there will be a complete collapse of the satellite, because whatever the micro crack happens in the beginning, over a period of time, it becomes macro and it becomes that leads to catastrophic failure. Therefore, these self-healing materials plays an important role in aeronautic industry and aerospace industries, because whatever it happens, it has to heal when it is very small. Self-healing materials can close the damage within the structure by restoring and maintaining its original mechanical properties, and that has a very big role in the coming days, because as the cost of maintenance is getting increasingly increasing drastically, exponentially increasing. Therefore, these self-healing materials plays an important role in the manufacturing industries. Whatever the self-healing concept, it should sense and actuate without the intervention of the human being. Material should gain some function, some fraction of the initial strength after healing. The example is our skin. You see here, when there is a cut in the skin, the blood starts. There is a blood clotting on the surface, and that starts healing up. So you see, this electric polymers. You can see here the first set of smart materials studied. Piezoelectric polymers are the first set of literature, and they convert in mechanical energy into electrical energy. And what are the applications of these polymers? They are used in inkjet printers, medical audio speakers, and then computer keyboards, and also in microphones. And what about the economic outlook? What is the money value of this material? As per the recent survey by the Material Society of India, Material Research Society in the world, that is MRS, there is $1 billion market. 75% includes piezoelectric polymers, 10% for shape memory polymers, 10% for self-healing materials, 5% for active fluids and phase change polymers. So let me give some of the glimpses of shape memory polymers. As I told you before, they memorize a macroscopic shape, they manipulate and fix themselves and relax, and they come back to its original position whenever it is required. So just see here. I will not go to history, and I will just try to give you the shape memory behavior. You see, the first step is to increase the temperature of a material to the glass transition temperature. Uh, just to in brief, the glass transition temperature means the material become the temperature at which material turns from glassy state to rubbery state. So you take any polymer, if you heat above glass transition temperature, the material becomes very soft, and then you elongate it. And the second step, third step is just cool it and fix it. And then the moment you heat the material to its original glass transition temperature, the material will come back to its original shape. So this is the shape. You see, if they heat the material to glass transition temperature, then the material will come back to its original shape. So this is the memorized shape of the material. The first one is stretching, second one is stretching and heating, second one is cooling down, and third one is clamp the distance and then heating up to glass transition temperature. Then the material will come back to its original shape. So how it works? So it works on the cross-linking density of the material. If the if it can hold all the chains in the material, then it's very easy for the material to hold it in the temporary shape. The moment you increase the temperature, the material becomes more and more amorphous, and then material tries to come back to its original shape. So this is there are several types in the shape memory polymers, amorphous, and so on. I'm not going in deep because the audience are very much heterogeneous. If anybody wants to have a deeper understanding, you can just write a mail, and definitely I will be very happy to share all these slides without any hesitation. So you see here the extension and cooling. This is the first figure. This is the fixing, and then the moment you heat it, it will come back to its original shape. This is very simple. Heat and stretch at the same time and then cool it. After cooling, if you heat the material, it will come back to its original shape. So what are these? You can see, yeah. Yeah, see here the one of the material which this is one of the video. Hope everybody is able to see it. And we were heating the material. So once we heat the material to above glass transition temperature, it is coming back to its original shape. Yeah, see, we deformed and then we cooled it, and when we heat the material to glass transition temperature, it came back to its original shape. And now there are two types of properties here. One is constrained recovery. The material under constraints, you try to recover the material, and the other one is free recovery. So just I'll skip these slides because may not be interesting. I'll just go to applications of shape memory polymers, how they are being used, where they are being used. These are some of the results obtained in our laboratories. And just skipping the designing aspect. uh, Yeah. So other aspect of 3D shape memory polymer is, they also give the opportunity to make 4D printing. Fused deposition modeling is a 3D printing of material using thermoplastic material. You just take this 3D thermoplastic material and you place it, and one layer over the other, that will give you a 3D printed structure. And there's a laser to cool it. The advantage of the rapid prototyping is, you don't have to waste a lot of your time. There is no need of mold or that a big injection big injection molding machine. But using 3D printing, you can, in single shot, you can prepare a 3D printed design. Only thing is, if you use shape memory polymers, so shape memory polymer gives another dimension. So therefore, you will be able to prepare all these structures through 3D printing, but it can also be 4D printing. You can see here, this is a printed structure, and whatever the printing we did, it is a first structure, and then if you cool it and deform it, it will come to temporary shape, and again if you heat, it will go back to its original shape. Therefore, it gives one of the one more functions, that is the 4D printing. We were able to make from 4D 3D to 4D, and that has a greater applications in days to come. And you see here, and this is one of the stunt which we were able to prepare, and the size of the stunt is getting enlarged. Yeah, that is the beauty of 3D printed structure. You can see here the first flower, and which was completely folded with temperature at at the human body temperature. We were able to exclude. We were able to make it fixed shape to a permanent shape. Yeah, these are all the designing aspect of the shape memory polymers. And then see here, yeah, this is the temporary shape. And when we were eating, the material is able to pick it up, and it can ship. So this can be another smart materials. And while using 3D printing, the wedge lock applications is also very important. And you see here, this is one of the aerospace application using shape memory polymers. This is the original one. The first one is the original one. The moment you heat the material, it can easily bend, and it can be easily transported to anywhere you want. And then the moment you reheat it, it will come back to its original shape. So it just goes there. It is being used as a deployable structure. And you see here, and to prepare sorry, aerospace wings. So just first one is takeoff, loiter, strike, and landing. So all these biomimetic structures we were able to make, so that the same structure can be used in aerospace using shape memory material. These are the same structure you can see for the morphing wing, and this is the shape memory morphing wing, and that can change its shape based on the requirement and also based on the temperature. And this is the automobile bumper. The bumpers are being, bumper are vulnerable for any kind of accident. And whenever there is a simple bump or something, earlier we used to change. Nowadays you don't have to change. Just if you put some hot water, it will come back. So what is the funda? Why it is coming back? Just because the polymer which is being used, it is just denting, it is deforming, and the moment you heat the material, it will reach glass transition temperature, and it is coming back to its original shape. So that is the way nowadays the bumpers, if there is a minor damage, bumpers can be a shape through shape memory applications. Bumpers can make smart bumpers. Therefore, the damage can be ignored and repaired very fast. And for example, nowadays, biomedical applications, nowadays, the doctors, whenever they use the pull-out strength of a secure anchor, it depends on the bearing area where it is increasing and so on. These wedlock are mechanically deployable within the skin layer of bone and provide the initial fixation. However, material can continue expanding over time due to thermal recovery to accommodate changes in the surrounding bone tissue. So you see here, the moment it enters the bone, it is changing its shape. So that means at body, it is the glass transition temperature of this suture, it is similar to the body temperature. Therefore, it is expanding inside, and once it is installed inside, it can be taken out very easily. Yeah, this is another applications in biomedical, that is orthopedic device, which is already commercialized. But anyway, the cost of that is nowadays is very high, but with time it may decrease. Yeah, see here, this is another biomedical applications of orthopedic device which we did through animal experiment. And so shape memory polymer is fixed here, and the moment it reaches here, see here, the first figure, we have kept very small one so that the placement will be very easy. And the moment it reaches body temperature, the moment the sample reaches body temperature, it is expanding on its own. Therefore, the healing will start, at 4 weeks. This is the morphology, microcity image, 8 weeks, and this is the 12th week. And also stent. There's a blockage of stent nowadays. The inserting the stent is a big headache, because that creates a lot of pain. Nowadays, patients are not having any pain because these shape memory stents are being inserted in a small, making it very small, smaller than the veins, and it is sent through the veins. The moment it reaches blocks, and it expands on its own, because the little bit laser light is given, laser temperature is given. The moment the temperature increases, it expands on its own, and the patients feel very much comfortable. And this is the mechanism here. You see here, this is the unrolling and unfurling. So unrolling, you see, this is the structure in the beginning. With the time, the unfurling of the stent starts. At the end, it reaches the unfurling, and the patient will be very much comfortable, even if there is a blockage, because it removes the blockage very easily. And nowadays, there are using acrylic copolymers, lenses are cast in a mold and cryolated to the desired shape. After reaching above constant temperature, the device is rolled to a diameter near 1.8 millimeter and then cooled below TG recovery time to receive between 3 to 25 seconds during deployment. These are called shape memory intercooler lines. This device will be triggered by body temperature to fit into the shape of the tear duct, because so nowadays, most of the people are using, particularly the young generation, contact lens. Why the contact lens? In the beginning, it irritates, and the moment it is fixed, it feels comfortable, because the moment from ambient temperature to body temperature, if it goes, it fixes on its own, and that creates that is very comfortable to the uh, patient, especially for those who are using contact lens. And this is very much important applications which has been published in recent times. This is the biomedical applications to remove growth. Here, the first one, this is the polymer that is given very short, that is destruction of enterogenesis, and once it is given, it starts enlarging on its own, and slowly this tissue also grows, and the enterogenesis can be minimized. So you see here it is enlarging, and with time it is enlarging, and this material is also, biomaterial is also enlarging. Once it is enlarged, it can be taken out. In that way, enterogenesis can be avoided, particularly in a patient who is having large intestine problems. uh, See here, this is another medical applications to remove blood clots in the brain. You just insert a shape memory polymer, and the moment it reaches the spot, it increases its size, because once it is inserted, this is the shape of the shape memory polymer. So, and with time, the shape memory polymer becomes like a spring structure, so that it takes out the, what do you call, the blood clot so easily, so that patient will feel very much comfortable. And again, this is aneurysm. Again, the same concept. When it is inserted, it is completely, packed, unfurled one, and it is slowly expanding on its own. And once it is expanded, the material the foam starts functioning as a biomaterial, and therefore the blood clots can be removed from the brain, and that creates, a lot of comfortness to the patients. So like this, there are a lot of applications which are already being implemented and it is being improved at the same time, because newer and newer materials are coming up. And this is one of the applications in composite structure. And we've also done a lot of modeling work on shape memory polymers to apply these shape memory polymers for various applications. And currently, these shape memory devices present here utilize one-way shape memory effect, and nowadays in the literature, we can see a lot of shape memory materials which are programmed to double, triple shape memory polymers, which have very good applications in the days to come. And also, we can also have, based on the existing studies, it is prospected that particle fillers, particularly for nanosized fillers, are widely used in the materials already, but they are not being able to commercialize because of the cost factor. In any case, extensive studies are needed on the relationship between the structures of shape memory polymers and their properties of the materials, requirements, specific applications, because this is very important. All the shape memory polymer cannot be used for all the applications. It is very specific. If you want to use it in aerospace, you need structural characteristics. If you want to use it in biomedical applications, you need biocompatibility, bioabsorbability, and so on and so forth. So therefore, we need both biologists, information scientists, as well as the chemist, particularly chemist, we require to make shape memory polymers or smart polymers more and more vibrant. I think I am done, Supriya Madam. And if there are any questions, I will be very happy to take it.
Okay. Any questions?
Sir, I have a question.
Yes, sir.
Sir, you told us that we can use the shape memory materials or healing materials in the aircraft, like satellites and all, right?
Yeah.
So they'll use the heating property, like if we heat them, and only then they'll regain their shape, right?
Can you please repeat? Yeah.
No, if a object is deformed,
Yeah.
if we heat that object, it will regain its shape, right? If we give some
Yeah.
energy.
Yeah.
So
That is
if we
only
are
in
set,
polymers. That is the case of polymers. The
yes,
the stimulus can be anything. It can be pH, it can be stress, it can be strain, or it can be temperature. It depends on the material. Whatever the aircraft I told, that is the self-healing material. Because self-healing materials are very important, particularly in aerospace industries. Suppose if there is any minor crack, suppose if you launch a satellite, okay. So if there is any minute drawback in the material, or there is any crack happens, in the midway, right? So over a period of time, what happens? The micro crack becomes macro crack. Macro crack leads to failure, and then there is a complete failure of the system. Therefore, whenever there is a micro crack, if if you have self-healing material, the self-healing materials can easily close it up. Therefore, the big accidents can be avoided.
okay. So like, how does the self-healing material work? Do we have to give them any energy in any way, or it
No, no,
just
no. Self-filling materials will have capsules in a strategic place. For example, where exactly the load will be more. You take any material. For example, if you take table, for example, in the legs load will be more. Okay.
yes,
So similarly, whenever you design any structural objects, you know where the load bearing capacity, or where the load falls on which region load is more, right?
yes, sir,
Hello,
yes, sir, yes, sir,
can you hear? So
yes,
in those strategic places, you need to put some capsules. The capsule contains the initiators, for example, or a healing material. Whatever the healing material you develop for that particular material. So the moment the crack takes place, this capsule will open up. Okay, then it
okay,
starts polymerizing or joining. Polymerizing means if it is polymer, if it is metal,
yes,
it should join two cracked metals, and
yes,
it
sir.
should be some kind of adhesive or some healing agent, something which is useful, or something which can fill the gap, or it can fill the crack. And that you need to develop based on the material.
Okay, okay, sir. Okay, sir, understood.
Yeah, you understand? Okay.
Yes, sir.
And skin is the best example of self-healing material, right?
Yes, sir.
Yeah. And similarly, because here, RBCs are self-healing material, they aid the healing of the skin. The wound healing
Yes,
is supported by RBCs, right?
yes,
So,
sir.
like that, you need to have something with respect to materials, because you need to develop for that material. For each and every polymer, it is different. If it is polypropylene, I need to have some propylene monomer with some initiators. So, the moment polypropylene starts breaking up, if I have monomer plus initiator capsule, they start polymerizing and they start filling the gap.
Okay, okay, sir.
Yeah.
Okay.
Any more questions? Okay. I think no questions. Okay. Okay, sir. I think no questions from audience.
Yeah.
Shall we conclude, sir?
Yes. Yeah, no problem. Yeah.
Yes, sir. Thank you. Thank you very much for accepting our invitation, sir, and for being with us for this enlightening us with your knowledge. Thank you. Thank you very much, sir. Thank you all for joining us today.
Okay, thank you for the opportunity. Hope
Thank you, sir.
everybody understood what is smart material at
Yes,
least.
it's a new concept that applications are very interesting, sir, actually.
Yeah. So I think if anybody wants any information on my research work or anything, you are welcome to write an email, or you can contact me through phone, or the way you want. I'll be very much open to discuss, and if possible, we can also collaborate, or we can visit colleges to enlighten what are the smart materials, how the smart materials are coming up in the market in the recent days.
What are the research going in your college, sir, in
Actually,
university?
we work on smart polymers, particularly piezoelectric polymers, energy generators, triboelectric nano generators, and also we also work on anti-cancer drugs, anti-cancer polymers, and the other topic we work on neurodegeneracy and then neurological problems. That is my colleagues. They work in our research center, that is Center for Research and Innovation, and of course synthesis of nanomaterials for various applications. Nowadays nanomaterials is not restricted to just one topic, right? Now
Yes.
you can use it for photocatalytic applications, biodegradation, and also biomedical applications such as antifungal, antibacterial, anti-cancer activity. So, and also on drug delivery applications. So it is a combination of everything: physics, mathematics, and computer science, chemistry, material science, engineering. So we have around 15 scientists in our research center of different disciplines, and everybody we works on different areas like this.
Yes, sir, very
And also
interesting.
we work on 3D printing. Yeah.
Okay. Okay. Thank you, sir.
Thank you.
Thank you. Thank you.
Thank you.
Thank you, one and all.